Seismic design is something we use on the West Coast, somewhat on the East Coast, more down toward the Carolinas. There's a seismic area, and if you look at Missouri and Utah, there's also seismic areas, but typically the West Coast. We look on the screen. The PGA is peak ground acceleration. The default is 0.2 G. There are some places on the West Coast. We get around Seattle. We're going to be around a 0.33 G. Some places in California might be up to 0.4 G. K vertical is a vertical component of seismic, typically assumed to be zero. When we have a seismic event, we have a horizontal acceleration and we have a vertical acceleration. They don't occur at the same moment. So we're going to design for the horizontal. We ignore the vertical. The vertical is about 20% of the horizontal. NCMA method and AASHTO methods currently use the horizontal displacement method, a Newmark method for analysis. If we have large horizontal displacements, default is 3 inches, then we would use these equations down here. For external, the displacement method is 0.0.75, A over D 0.25, a lower value. The internal for NCMA was based on, not on a stiffness method, it was 1.45 minus A, which is a calculated value, times the acceleration, and that would be 0.42. In most cases, we're going to use the displacement method. If we have zero displacement, you can see both of these numbers change to the old method. A over 2 for external, 1.45. If we have 2 or 3 inches of displacement, then we see we drop considerably on these numbers. The enable button says to enable seismic design or not enable seismic design. If we go 0.2 G, really doesn't have much of an impact on design. If we look at here, go back and I'll go back to the Cornerstone 100, Stratagrid reinforcement, horizontal design. We have, this is better. There's 1 foot beyond the failure plane. That's what we're looking for. We see our sliding and overturning. We enable seismic. The seismic results are empty, but we update the design, and now you can see that our static 4.24 and overturning 2.3 and sliding, seismic 2.85, so it's quite a bit lower, and overturning sliding 2.29 versus 2.39. So we have a seismic force behind it driving the mass forward. We have inertial force internal driving forward, and then we also have the inertial force of the face driving forward, putting more tension on the connection. As we come across the table, you can see our Tmax value and the Tmax MD, the seismic component, are quite a bit different, and the factors of safety with seismic, without seismic, the peak connection, static peak connection with seismic. Factor of safety pullout tends to be a problem on the top grid because of the load that we have up here versus the overpressure holding back. We can solve that by going on the first grid, lengthening our G-grid. There we go. We'll lengthen the geogrid. Whoops. Hit the wrong character. We can lengthen the geogrid, and then that factor safety comes back. We shorten the grid back down. We can see that we're failing both static and dynamic. We'll lengthen it 1 foot past the failure plane. We're passing static. We're failing dynamic. Personally, I'm not too concerned about the top grid. What the theory says is it's 1 foot beyond the failure plane, and then we calculate the tension on that grid from the surface to halfway to the grid below. That applies it to that grid, and then we look at the pullout of that individual layer. What I look at, and what the British standard BS 8706, is when they looked at pullout, they look at the total pullout beyond that failure plane of all the grids compared to the driving force. And that's what we've done down here. Total pullout capacity, we got 5,600 pullout capacity. We've got a factor safety of 5.19. If I shorten that top grid down further, it doesn't pass the failure plane now. The top grid is failing in pullout, we've already seen that. But the overall pullout is still over 5.2. So that wedge of sole cannot fail. The top grid cannot fail. The failure plane for that upper course would be about like that. So we have plenty capacity behind it, going from the bottom to the top. Conservative, not realistic. Even in seismic, your total pullout capacity is 7,600. Factor safety pullout 3.97. So again, the programs that tell us we don't meet the factor safety and pullout on the upper grid. If we look at the overall pullout engineering judgment, it does. So in this case, I would personally say by engineering judgment, the design is okay. That's it on seismic. Again, if we have zero displacement, then we're not looking at displacement methods anymore. We look at the ACE of M value of 0.25. If we have displacement, then those numbers change, 0.83 down there versus what we had before, 0.1. Quite a bit of reduction in there. So the default value is 3 or a variable of 10 times the PGA, which is again is going to be 2 to 3 inches. That sums up all of our input screens. Now we'll go on and we'll look at some of the output results.